So let's illustrate this with a couple of examples. Let's look at page 300, number 8, and page 300, number 14. These are pretty lengthy. The book has several worked examples as well, so I refer you to examples 4, 5, and 6 for even more of this stuff. But these two examples give us some idea about the dynamic behavior of this stuff. And number 8 gives us a 3x3 matrix. And instructions are: find the characteristic polynomial, the real eigenvalues, and the corresponding eigenvectors for 3x3 matrix A. Okay. Well, first, we're definitely interested in A minus lambda I. We're always interested in A minus lambda I when computing eigenvalues and eigenvectors. Of course, all that happens when we take scalar lambda times matrix I is we pick up these lambdas along the diagonal, zeros everywhere else. So when you do the matrix arithmetic, you just have the original matrix A with lambdas subtracted along the diagonal. So we'll see lots of that. We saw an example like that actually in the section on determinants, where for some reason we were taking the determinant of a matrix that looked somewhat like this and setting it equal to 0. That was to foreshadow exactly the computation of eigenvalues. Okay, now the characteristic polynomial by definition is P of lambda is the determinant of A minus lambda I. So we'll take the determinant of this little modified matrix here. Let's expand along the first row because of the 2 zeros there. Easy enough, we'll have -1 minus lambda times the determinant of the minor matrix, minus 0 times something, plus 0 times something. That's why we chose the first row. And it just requires us to take the determinant of this 2x2 minor matrix, go along the diagonal, multiplying, subtract what you get by going along the off diagonal, and that produces this polynomial. Actually, because of the zeros, it turns out the polynomial is already factored. We'll want to find the characteristic polynomial, and we'll want to factor the characteristic polynomial. Now, next, we'll set the characteristic polynomial equal to 0. So the lambda values that'll make it 0 are the lambda values that make the first term 0, or the second term 0, or the third term 0. That would be lambda is -1, lambda is 2, and lambda is 3. So the eigenvalues are -1, +2, and +3. Got the characteristic polynomial. This is always the recipe to follow for characteristic polynomial. For eigenvalues, always set the characteristic polynomial equal to 0. That produces the 3 eigenvalues. I said in passing, let's list some eigenvalues in increasing order. There's a first one and a second one and a third one. -1 is less than 2 is less than 3. So order doesn't matter. But to be consistent, I'll always list them in increasing order because we ain't done with those eigenvalues and we're going to have to do some stuff with them. That stuff is the last part of the question: find the corresponding eigenvectors. Okay. So to find the eigenvectors, we need, the definition was, we need AV to equal lambda V for this lambda value, that lambda value, and the other lambda value. That's equivalent to, as we commented in the notes, the homogeneous system of equations, A minus lambda I times vector V equals 0, where we're choosing a specific value for lambda. And then we'll have specific values for the components of V. Okay. First, lambda 1 equals -1. We'll let vector V sub 1 be a corresponding eigenvector. We'll get the form of vector V sub 1 out of all of this. Let the components of V sub 1 be V sub 1, V sub 2, V sub 3. Sorry about the repetition on the V sub 1 stuff, but we've got lambda 1, the first eigenvalue, so it's reasonable to denote the corresponding eigenvectors of the form V sub 1, vector V sub 1. And we'll probably just recycle these components, V1, V2, V3, because we're going to have to do this 2 more times for the other 2 eigenvalues. So we're interested in solving the system of equations A minus lambda 1 I V sub 1 equals 0, where lambda 1 is negative 1. All right, so we'll plug negative 1 in for lambda. We've got the coefficient matrix, A minus lambda 1 I. There you go. Original matrix A with minus negative 1 along each of the diagonal elements, augmented with 0 because it's a homogeneous system of equations. I guess I really don't have to keep up with these zeros on the right-hand side because they ain't ever going to change with the row reduction. But it'd be consistent with the way we dealt with systems of equations. I'm going to augment it with the zeros. So doing the arithmetic, that produces this augmented matrix, and anything catch your eye? Yeah, a row of zeros. Okay, so how many pivots does this have? Well, if it's got a row of zeros, it's got at most 2 pivots. It can't have 3 pivots. In fact, I think it'll have exactly 2 pivots. Is that right? Yeah, that kind of thing's always going to happen, because if we had 3 pivots, then we'd have a unique solution to the system of equations. What is a solution to the system of equations always when it's homogeneous? Well, the 0 vector. We can't use a 0 vector. By definition, eigenvectors are not the 0 vector. So we're going to get multiple solutions. Yeah, guaranteed. That's where the lambdas came from. So these 3 eigenvalues, I guarantee you, will produce associated systems of equations, homogeneous systems of equations, that have multiple solutions. If they don't, you ain't really got eigenvalues. So if you don't have free variables that result from this, something's wrong. My first guess is what's wrong is you don't have the right eigenvalues and you messed up something upstairs. So here's the matrix, system of equations. Let's do a row reduction thing. In the video, let's kind of skip past the details on that. It's in the supplemental notes. And it looks like that produces a row equivalent augmented matrix of this form. Yeah, no pivot in the 3rd column. So that'll mean a free variable replacing the 3rd variable. Returning to a system of equations that produces the corresponding system of equations here. V1, V2, V3, aligned as usual. Solving for V1, V2, V3 from these 3 equations produces this. The 0 equals 0, pivot free 3rd column produces V3 equals V3. So we'll let R equals V3 be a free variable. We get everything in terms of that free variable. V1, V2, V3 expressed in terms of R of this form. We're looking for a vector. So let's express that vector as a span or as a scalar multiple. So the collection of all eigenvectors of lambda 1 are any vector v1 of the form r times -1, -1, 1. So the scalars by which r is multiplied to produce the components are respectively -1, 1. And if we'll take any scalar multiple, except for 0, because 0 doesn't count, the 0 vector doesn't count as an eigenvector. But if we'll take any scalar multiple of this, then we're good to go. So that's the collection of eigenvectors corresponding to eigenvalue lambda sub 1. They wanted all eigenvectors. We got to do this 2 more times for the other 2 eigenvalues. Next, let's take lambda 2 equals 2. Okay, now we want to consider the homogeneous system of equations, a minus lambda 2 I, v sub 2 equals 0. Lambda 2 was 2. So we'll take matrix A, subtract lambda 2, subtract 2 along the diagonal. We'll produce this matrix here, and I notice a relationship between the 2nd row and the 3rd row. That'll be producing somewhere downstream a row of zeros and a pivot-free column. So we'll do the row reduction thing. There's the details spelled out on the slide. It produces this matrix, pivot-free column, in the second column. So we'll have a free variable corresponding to that. Converting it back to a system of equations, we get V1 equals 0, V2 equals 0, 0 equals 0. I have no information about V2, so we'll take that to be a free variable. V1 is 0, V3 is 0, V2, say, is a free variable. Let's call it S. We used R last time, so for variety and variables, let's use S. Any vector with components V1, V2, V3, as given here, where S is any real number except 0, will produce an eigenvector corresponding to lambda 2 equals 2. So we get all multiples of, read the coefficients of S off, 0, 1, 0. Oh, and we can't use S equals 0 because the 0 vector isn't an eigenvector. Let's do it again. So same thing, except now with lambda 3 equals 3. We'll consider the system of equations, produces this. Simplified, we get something like this. I noticed something between the first and the third rows. We do a row reduction thing. Sure enough, there's a free variable. This time it looks like it's in the third column, pivot free column. So the third variable will correspond to a free variable. Convert this back to a system of equations. Solve for V1, V2, V3. We get things in terms of V3 because the third column was pivot free. We'll let maybe T be a free variable this time. Let T equals V sub 3 be a free variable. That'll produce V1, V2, V3 of this form. So that gives us the components, again, of eigenvectors, this time associated with eigenvalue, lambda sub 3. And so the associated eigenvectors are any scalar multiple other than 0 of, read the coefficients of T off, 0, negative 1, 1. So the collection of eigenvectors associated with lambda 3 is given here, with the other lambda values is given above. So 3 by 3 matrix, the characteristic polynomial, it was a third degree polynomial, as was mentioned in the notes, and we got 3 different lambda values, each one having, in some sense, up to linear independence, having 1 eigenvector. These collections of eigenvectors, if we treated them as spans, to do that we'd have to let T equal 0 then. We'd actually have little one-dimensional vector spaces. They're called eigenspaces here shortly. But we got 3 linearly independent, I think they are, linearly independent eigenvectors for 3 by 3 matrix, 3 eigenvalues. The books seem kind of balanced with all that 3 stuff, 3 by 3, 3 eigenvalues, 3 linearly independent eigenvectors. Other stuff can happen though. So let's take a look at number 14. It says find the characteristic polynomial, the real eigenvalues, and the corresponding eigenvectors for this matrix. Okay, just like the last one, instructions-wise, just like the last one, we'll have to consider A minus lambda I. So that's taking matrix A, ultimately subtracting lambda along the diagonal. You want the characteristic polynomial, then take the determinant of A minus lambda I, because that's the definition. Again, as in the previous one, let's expand along the first row because of the 2 zeros there. We'll have 4 minus lambda times the determinant of the minor matrix. Okay, minus 0 plus 0 because of the 0 entries. That's why we chose the first row. We'll do our determinant of a 2 by 2 matrix deal. And I'll give us 4 minus lambda times 4 minus lambda minus 0. Giving us 4 minus lambda times 4 minus lambda times 4 minus lambda. The 0's gone. That's 4 minus lambda cubed. It's a third degree polynomial. We've got a 3 by 3 matrix. That was predictable. So there's a characteristic polynomial for eigenvalues. Set it equal to 0. Set that characteristic polynomial equal to 0. And we only get 1 eigenvalue this time. We get the eigenvalue 4. It kind of counts 3 times. It's associated with 3 factors. All those factors are the same. That's why we only get 1 eigenvalue. It's said to have algebraic multiplicity 3, because if I were to count how many times 4 is a root of the characteristic polynomial, it would be 3, if you recall how you count algebraic multiplicities or multiplicities of roots of a polynomial, maybe from high school or from pre-calculus. So there's a 3 somehow associated with this, even though I only see one eigenvalue. Let's go looking for eigenvectors. Okay, so as before, we'll consider the associated system of equations. A minus lambda I times vector v equals 0. And we got to do that for every eigenvalue, but there's only one this time. So we only have to go through the system of equations stuff once this time, because there's only one eigenvalue this time. All right, system of equations, a minus lambda I. So we'll take a, subtract lambda equals 4 along the diagonal. We'll produce this matrix. We're considering a homogeneous system of equations. Okay, easy enough. We'll swap row 1, row 2, and get that factor of 8 out of the way. Produces this row reduced echelon form associated with the original system of equations. Pivot-free second column. Ooh, pivot-free third column as well. That's not a pivot. We'd have to go down and over to find another pivot. So second and third columns are pivot-free. I knew that was going to happen as well. Well, I knew there'd be multiple solutions. I didn't know how many pivot-free columns it would be until we did the arithmetic. But you know we're going to have multiple solutions. If you don't, something's wrong. You always have multiple solutions when you're computing eigenvectors. Because if there ain't but one solution, it's going to be the 0 vector. And the 0 vector is not an eigenvector by definition. Okay. Write that as a system of equations. Rewrite it as V1 equals V2 equals V3 equals. We got V2 and V3 acting as free variables. Well, I knew that was going to happen as of the last slide because we had the second and the third columns pivot free. So we'll let R equal V2 and S equal V3 be free variables. Then we can rewrite V1, V2, V3 in terms of R and S. So we'll pick off the coefficients of S and the coefficients of R and take multiples of the resulting vectors. The coefficients of S are respectively -1, 0, 1. Coefficients of R, no R's, 0, 1 R, 0 R's. So any vector of the form R times 0, 1, 0 plus S times -1, 0, 1. R and S can be anything. They just can't both be 0 or we'd produce the 0 vector. Then we have an eigenvector associated with the only eigenvalue this matrix has, 4. So the books kind of didn't balance on this one. I'm foreshadowing some behaviors of eigenvectors. In this case, we only had 2 linearly independent eigenvectors. Say this one and this one, or a scalar multiple of this one and a scalar multiple of that one. So we only had, for a 3 by 3 matrix, 2 linearly independent eigenvectors. In that last example, 3 by 3, 3 distinct eigenvectors and 3 linearly independent eigenvectors. So in some sense, there's something a little wrong with this one. It should have another eigenvector or something. So there's something inferior about this matrix A. It isn't as complete, and I'm making these words up, it isn't as complete as the example we saw in the last one, but this is something that can happen with eigenvectors. And the good news in this one is, geez, I only had one eigenvalue, so I only had to consider one system of equations. It ended up having 2 free variables, but that kind of covers the ways that computations of eigenvalues and eigenvectors can behave. Back to the notes. Let's look at the next theorem, and let's even look at the proof of a piece of it. Properties of eigenvalues and eigenvectors. Let A be an n by n matrix. we wouldn't have a conversation about eigenvalues and eigenvectors unless we had a square matrix. They're defined in terms of determinants. You can only take determinants of square matrices. You can only take inverses of square matrices. So we haven't exclusively restricted ourselves to square matrices, but more often than not, we were dealing with square matrices. We talk in eigenvalues and eigenvectors, got to be square matrices. First claim is, if lambda is an eigenvalue of matrix A with V as a corresponding eigenvector, then lambda to the k is an eigenvalue of matrix A to the k power, again with V as a corresponding eigenvector, where k can be any natural number, any positive integer. So for example, if V is an eigenvector of matrix A corresponding to eigenvalue lambda, then V is also an eigenvector of matrix A squared, but corresponding to eigenvalue lambda squared, k equals 2. Secondly, if lambda is an eigenvalue of an invertible matrix A with V as a corresponding eigenvector, and if lambda is not 0, remember, we didn't say eigenvalues couldn't be 0. We said eigenvectors can't be 0. So we have to add this as a hypothesis, because under these hypotheses, 1 over lambda is an eigenvalue of A inverse with V as a corresponding eigenvector. And we'll go through the proof of that one, and it can't be harder. We wouldn't have to go through the proofs of them. The proof of the first and third are left as exercises in this section. Thirdly, if lambda is an eigenvalue of A, then the set E sub lambda, consisting of the 0 vector together with all eigenvectors of A associated with eigenvalue lambda, is a subspace of n space of Rn. It's called the eigenspace of lambda. Now that last example we had was exactly that, where we had 4 as an eigenvalue of algebraic multiplicity 3, and we had 2 linearly independent eigenvectors associated with that lambda equals 4. We had the free variables, the r's and the s's. So if we took all linear combinations in that last example and threw in the 0 vector, because we couldn't include the 0 vector because in that question we were looking for eigenvectors, and the 0 vector doesn't count as an eigenvector. We had a 2-dimensional subspace there. Take a quick look at it, because I think it was the last thing we had displayed. Yeah, for lambda equals 4 for that matrix, this was the collection of all eigenvectors associated with that. And we didn't allow R and S both to be 0 because we didn't want to include 0. If you would include 0 with this collection of vectors, 0 vectors still not an eigenvector, but if you included it with this collection of vectors, you'd have a 2-dimensional subspace of R3. Yeah, that 2-dimensional subspace is the eigenspace of that matrix associated with lambda equals 4. In the example we did before that one, we had 3 eigenspaces. They were each 1-dimensional. We had really the span of a single vector, except we didn't allow the 0 vector because we were finding eigenvectors then. But if you'll include the 0 vector, you actually get little subspaces of Rn. Let's look at a proof of part 2. Okay, let's prove if lambda is not 0, then 1 over lambda is an eigenvalue of A inverse, and it has as a corresponding eigenvector vector V, which was also an eigenvector of matrix A. All right, first off, if lambda equals 0, I'm trying to get an implication of what happens when lambda doesn't equal 0. If lambda does equal 0, is an eigenvalue of matrix A, then there's a non-zero vector V such that AV equals lambda V. That's what an eigenvector is by definition. If lambda equals 0, we're getting the 0 vector out. But then we've got a homogeneous system of equations. If we look at the equation, A times vector V equals 0, and this has a non-trivial solution. But That only occurs, I guess it was theorem 16, when matrix A is not invertible. But we're told that lambda is an eigenvalue of an invertible matrix. Well, if lambda equals 0, we don't have an invertible matrix. All right, then up here, we must not have lambda equals 0. If we did have lambda equals 0, we wouldn't have an invertible matrix. All right, so the first claim was, if lambda is an eigenvalue of an invertible matrix A, blah, 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 then lambda is non-zero. There's an argument that under these hypotheses, lambda must be non-zero. Next, for the computational part, if lambda is an eigenvalue of matrix A with corresponding eigenvector V, that means by definition, AV equals lambda V. We know A is invertible, so let's multiply both sides of this equation by A inverse. So A inverse, AV equals A inverse lambda V. We can rewrite that. Take that scalar. Scalars pull through the verbiage that Fraley and Beauregard use. I can bring that scalar out front. Ooh, A inverse and A, that'll produce the identity matrix multiplied times vector V, gives us vector V. And we get V equals lambda times A inverse V. Remember where we're going. We're looking for eigenvalues and eigenvectors of A inverse. Let's take this little equation and divide both sides by lambda. That'll give us A inverse V. Take the lambda to the other side as a 1 over lambda. A inverse V equals 1 over lambda V. Well, there's where we've got a matrix. The matrix is A inverse times vector V equals some scalar multiple of vector V. Dude, that's an eigenvalue and a corresponding eigenvector for the matrix, the matrix A inverse. So this little equation here explicitly means 1 over lambda is an eigenvalue of A inverse, and vector V is a corresponding eigenvector. And that's what we were trying to show. So here's some little properties of eigenvalues, probably not of great computational interest, but certainly of interest if you dig deeper into matrices. Next, we'll look at dealing with linear transformations. You might recall, if you've got a linear transformation from Rn to Rm, then you got a matrix. Linear transformations in that setting were always associated with matrices. Ooh, and I know how to find eigenvalues and eigenvectors of matrices, so we should be able to find eigenvalues and eigenvectors of linear transformations. So let's do that in the next part of the video.